With any empirical method, it's important to recognize the situations where it's useful. There's no free lunch in econometrics, and sometimes the assumptions behind the fancy empirical method are worse than the assumptions behind the simple one. In this video, I'll start by describing a situation where the linear regression model might not be up to the job, and how a method called instrumental variables, or IV, can solve the problem. I'll lay out the intuition behind IV and explain what makes a good instrumental variable. I'll explain the basics of estimating a causal effect using an instrumental variable and some of the potential pitfalls. At the end of this video, you should be ready to critique other people's instrumental variables and come up with candidate instrumental variables of your own. In short, you'll be ready to read work that uses the method and start work of your own. Suppose you're interested in estimating the causal effect of a year of education on wages. One way to do this is to estimate a Mincer equation, that is a regression model where log wage is a linear function of education, experience, and experience squared. Now in this model, is it reasonable to assume that the expected value of the error term is independent of education and experience? That is, are there unobserved determinants of wages that might be correlated with how much schooling someone gets? I suggest pausing the video now and making a list of those potential determinants. I'll wait. Okay, now I can't see your list, but here are a few things that might have a direct effect on wages and might also determine how much schooling you get. What about intelligence? Certainly, smarter people tend to get higher wages, but those smarter people also tend to get more education because getting education is easier for them. Persistence, or how hard somebody's willing to work, is another characteristic that might be a determinant of wages, but might also determine how much education you get. People in good health tend to get paid more and complete more years of schooling. And similarly, people with good social networks or connections tend to get better jobs, ones that pay more, and they may also be able to get into better schools and complete more years of education. If we don't control for these potential confounders, then this won't be true, okay? And if that's not true, that means education is endogenous, and the OLS estimate of beta 1 is going to be a biased estimate of the causal effect of schooling. Now, if we had measures of all these things, all these potential confounders, and we could control for them, that would address the problem. Unfortunately, most of these variables, they aren't in the big public data sets that economists like to use, and they're pretty hard to measure even if we wanted to collect our own data. IV is a method that accounts for this endogeneity without having to actually measure these variables. Now what we want to do is, instead of just using OLS, we want to restrict ourselves to just some of the variation that we see in education. We want to use just the variation in education that's not correlated with our error term. One way to do this would be to run an experiment. Suppose we took a random half of your sample and we forced them to get exactly one more year of education. Well, we could compare the wages of that treatment group to the control group, and the difference is going to be the effect of a year of education on wages. With IV, what we're doing is we're trying to find something that naturally induces this kind of exogenous variation. Now, an instrument we're going to define as a variable that determines the endogenous regressor. In this case, that's education. Endogenous regressor is education. And the instrument determines the endogenous regressor, but it only affects the dependent variable through its effect on the independent variables. Now, when we say it only affects the dependent variable through its effect on the independent variables, what we're saying is that z, which is what I'm going to use as notation for an instrument when I don't want to talk about a particular instrument, we're saying z is independent of the error term. It only affects wages. So here we're saying our instrument, whatever instrument we choose, it can only affect wages through its effect either on education or experience. Now let's think about a couple examples. Does distance to the nearest college, at least in part, determine how much education someone gets? Sure. People who grow up close to a college are more likely to go because the cost is lower. It's closer. Now, what about the second key part of it, a good instrument? Does distance to nearest college have an effect on an individual's wage that doesn't go through education or experience? Well, maybe, maybe not. If we think labor markets in areas with universities are substantially different from areas that don't have universities, then distance to nearest college is a poor instrument. If we think those labor markets are pretty similar, well, then maybe the instrument is okay. Now, let's consider the quarter of birth, the quarter of the calendar year that someone was born. Now, why might the quarter that you were born determine how much schooling you get? Well, many states require kids to be 6 years old by the end of the calendar year in order to start first grade. That means kids born in the first quarter of the year are usually the oldest kids in the class. Those 1Q kids are the oldest kids. Now, if you read Malcolm Gladwell's Outliers, you might think that this means those kids do better in school because they're more mature and thus they go on to get more schooling. But you'd be wrong. This effect might exist, but it's outweighed by another bigger effect. Many of those older first quarter kids are able to drop out of school when they turn 16 before the end of their junior year in high school. And thus they only complete 10 years of schooling. The kids born in the third and fourth quarter of the year are not legally allowed to drop out until after they've completed their 11th year of schooling. Now, do we think quarter of birth has a direct effect on wages? An effect that doesn't go through education? Probably not. On the surface of it, this would seem to make quarter of birth an excellent instrument. But unfortunately, the correlation between quarter of birth and education turns out to be just too low for the IV estimates to be reliable. And I'll say more about that in a little bit. So how does IV work? Well, first we need a good instrument. And that means an instrument that's correlated with our endogenous variable, like education, first. And second, a good instrument has to affect the dependent variable only through its effect on the endogenous variable and the other independent variables. It cannot have a direct effect. So let's go back to our returns to education example. We can think about education, the endogenous variable, as being composed of three different parts. The first part, the part we don't like, is the part that's correlated with the error term. The second part is the part that's correlated with the instrument, say distance to nearest college. That is, the part that is induced by being close to a college or not being close to a college, since we're considering that to be independent of the error term, distance to nearest college. And then the third part, we don't care about this at all, is the part that's not correlated with the error term, it's not correlated with the instruments. What IV does is it allows us to only use the part of education that's correlated with the instruments when we estimate returns to schooling. We're going to implement that insight in a particular method called two-stage least squares. Okay, we start out with the original regression model. Now we can't just use OLS or ordinary least squares to estimate this, because remember that education is not independent of the error term. And that means that our expected with OLS, beta 1 hat OLS, the expected value of that is not beta 1. That's a not equals. It's not beta 1. It's a biased estimate. So what we're going to do is we're going to break this into two pieces. Okay, the first piece, which we're going to call the first stage, we're going to regress education, our endogenous variable, on the instruments and the other independent variables. Okay, we know that this is valid, okay, and we know that we should get something interesting here because Z is a partial determinant of education. Say distance to nearest school partially determines education. Okay, so we estimate this. Then we use our estimated coefficients, in this case our gamma hats, to predict out education for every individual in our sample. Okay, these estimates are unbiased estimates of education itself. Now, another interest, so we can use this. We can put education hat right into our regression. It's an unbiased estimate of education itself. The other thing to recognize is that this predicted education is a linear combination of our instruments and our other independent variables. Because each of these is assumed to be independent of epsilon, the linear combination must also be independent of epsilon. And so we know that education hat is uncorrelated with epsilon. And so we can plug education hat into that original model, replacing education itself. And when we estimate this model, our estimate of beta 1 hat is going to be an unbiased estimate of beta 1. And that's the magic of IV. Now let's take a look at an example of IV in action. In 1993, David Card wrote a paper called Using Geographic Variation in College Proximity to Estimate the Return to Schooling. He instrumented education using a dummy variable that was equal to 1 if someone grew up in an area that was near a college. Now, in his first stage, he regressed education on this dummy variable, and he found it was a very significant determinant of schooling. For this estimate, he did not control for family background variables, and for this one he did. Turned out not to matter much. He got almost the same point estimates in both cases. What he found was that individuals that grew up near a college completed on average about 0.3 more years of schooling, and it was a very significant effect. Now in his second stage, he used these coefficients to predict out education for everyone in his sample, and then regressed that predicted education on log wages, regressed log wages on that predicted education. And what he got was an estimate of 0.132, or rather, he estimated that a year of education would induce a 13.2% increase. Each year would induce a 13.2% increase in wages. Now, one of the most important things to worry about when you're doing IV is that your instrument is sufficiently correlated with your endogenous variable. This turned out to be a serious problem with the quarter of birth as an instrument for years of schooling. A rule of thumb that many people use now is that they do an F-test on the null hypothesis that the coefficients on the instruments in the first stage are 0. The F statistic for this test should be at least 10 and preferably 12 for the instrument to be strong enough to use. Now in 1995, Bound, Yeager, and Baker published a paper that showed that quarter of birth, if you do these F tests, you get values of 2.4 and 1.87, depending on which specific model you use, and those are obviously a lot lower than 10 or 12. Now, there are 3 more important things about IV that I want you to know. First, you can use multiple instrumental variables at the same time. That is, your instrumental variables can actually be a set of variables, as long as they each meet the criteria of being good instruments. Second, IV does not give you the average treatment effect. If you think that the treatment effect is different for different people in the sample, that can be a problem, okay? Because what IV does is it gives you the local average treatment effect. That is the average treatment effect just for the group that's actually influenced by the instrument. For example, when we looked at distance to nearest school as an instrument, what we get with the IV estimate is only the estimate for the individuals that were affected by it. That is, the individuals who would attend college if one was local, but otherwise wouldn't attend. If you think this group might gain more or less from a year of college than individuals that would go to college no matter what, then the local treatment effect is going to differ from the average treatment effect. Third, the two-stage least squared procedure I just told you about gives you the right point estimates, but you have to be careful in computing your standard errors. If you just plug your predicted values from the first stage into the second stage and run OLS, you'll get the wrong standard errors. If you use Stata, you can use the IV regress command to get the corrected standard errors. So the bottom line is that IV estimates are only as good as the instruments that are used, and there are many ways in which these instruments can be lousy. Weak instruments don't work well, but at least you can assess this just by looking at the results of your first stage. If an instrument has a direct effect on the dependent variable, one that doesn't go through the endogenous variable or the other variables in your regression, then your instrument's not valid. This is a very hard thing to test. The one exception is that when you have more than one plausible instrument, you can do something called a Sargon or a Wu-Hausman test. And the intuition behind these tests is that if you use your instruments individually, they should give you very similar answers if they're both good instruments. If you get different answers, then something's wrong with one of them. Unfortunately, it's often pretty hard to find even just one plausible instrument.